Hi, my name is Kim King, and I'm here with my teammates Ethan Barron and Servando Calderon Felix to share with you our senior design project, the Augmented Reality Ultrasound with Holographic Needle. Ultrasounds are one of the most popular tools in medical technology today due to their affordability, effectiveness, and non-invasive nature. In just one decade, the use of ultrasound rose almost 40%. However, the nature of ultrasound images can make them difficult to interpret. In fact, 3 to 5% errors occur daily due to incorrect interpretation of ultrasound data. One of the most popular uses for ultrasounds are in ultrasound-guided needle procedures, such as nerve blocks, which are the type of procedure that we mainly focused on improving with our project. Nerve blocks are a type of regional anesthesia that uses ultrasounds to guide the needle as close to a nerve or group of nerves as possible in order to inject medication. While common, these nerve blocks are not a simple procedure. They have a steep learning curve for medical students since they require complex multitasking, where the clinician must maneuver both the needle and ultrasound probe at the same time, all while focusing on an ultrasound image on a machine far away. It can be very difficult to interpret the ultrasound plane on display because it's only a 2D image and requires the clinician to discern the orientation of the anatomy while the image is constantly changing to the motion of the probe. In addition, even with the best echogenic needles on the market, the needle tip can be difficult to see on the ultrasound throughout the procedure. If done incorrectly, there is a risk that the clinician contacts the nerve with the needle, causing the patient to actually jump in response. Other complications could include an incomplete reduction of pain, bleeding, damage to the surrounding tissues, and/or infection.
As Kim mentioned, there are several critical issues with current ultrasound-guided procedures. Our senior design project seeks to solve these issues by generating a program that is able to take 2D real-time ultrasound data and generate a 3D volume. Additionally, we opted to improve the visualization and tracking of an echogenic needle with a digitally rendered one. Overall, the goal of our project was to develop and merge these two components to generate a hologram of the volumized ultrasound data and rendered needle in augmented reality using a head-mounted display. This allows for a more accessible, intuitive way for physicians to utilize ultrasound technology to safely guide echogenic needles in procedures such as nerve blocks. Throughout the lifecycle of the project, designing for intuitiveness and compatibility was of paramount importance. It was critical to ensure that the product made interpreting ultrasound data easier for clinicians and that it would be able to be compatible with existing ultrasound equipment and accessories. This means that it must be able to retrieve ultrasound data from third-party ultrasound machines, and that any alterations to the current physical design of either the ultrasound probe or echogenic needle did not hinder the user's ability to use the device. This image represents the flow of information to and from all of our major components. You can see that the location of the ultrasound probe is tracked by using overhead Vive sensors that will transmit the positional data to the computer for processing. This computer then uses this positional data in conjunction with the 2D ultrasound images to generate a 3D volume that can be seen through the HoloLens 2 headset. The fiducial that is attached to the echogenic needle is tracked via cameras inside the HoloLens 2. These cameras determine the orientation and location of the needle fiducial to then project a holographic needle in line with the physical one. The final result will be a holographic needle and ultrasound volume that aligns with patient anatomy and an actual echogenic needle and can update in real time.
Shown below are examples of the rendered ultrasound volume. The image on the top demonstrates how the image trailing works. On the right side of the image is a live ultrasound feed that is being displayed on a single quad. The left side shows how this quad is converted to a volume by stacking the frames. The trail of frames is left behind when the user removes the leading plane, which displays the live ultrasound feed. The distance between each frame is defined by the user, so one can make the volume denser or sparser depending on the situation. The image in the bottom demonstrates the post-processing done on the volumized image. And as you can see, the software makes the black portion of the ultrasound transparent. This is done to highlight the relevant anatomical structures, making the ultrasound easier to interpret. This also helps the user see the needle inside the ultrasound volume. The rest cylindrical object is a pseudoneedle that can be clearly observed going into the vein that is shown in the ultrasound. The transparency can be changed by the user to make it more opaque or more transparent depending on their needs.
When determining the best way to track the needle during the procedure, the first thing I had to consider was the Vive tracking system that last year's team implemented to track the location of the ultrasound probe. Since it wasn't possible to use the same tracking system for the needle due to the size of the Vive tracker, I had to determine what could be used that wouldn't interfere with the current system and wouldn't add a lot of additional hardware. Thus, I decided to go with a camera-based tracking system that utilizes the built-in cameras of the HoloLens headset. To do this, I discovered the Vuforia Model Target software that recognizes and tracks objects in the real world based on the shape of the object and display a hologram once the object is detected. This is done by uploading a 3D model of the object you want to track. In this case, it was the black fiducial seen on that image to the left, as well as a 3D model of what you want displayed as a hologram. In this case, it was a simplified render of the needle shaft shown in gray on the left. This design of the fiducial was specifically created to have a unique and complex geometry so the Vuforia software could easily detect it, but simple enough to be 3D printed easily. Additionally, it was designed to be able to snap onto a standard needle handle easily and be relatively unobtrusive during its use. The whole fiducial adds less than 4 grams total and adds 2.5 inches in height. The bent shape was intentional so that the added height would not contact the ultrasound probe, and it would also allow enough clearance for the hand holding the needle. Additionally, it also helps to clarify the direction of attachment. Overall, this design allows for a cheap and effective way to track the location and orientation of the echogenic needle to allow for better visibility during the procedure.
While there are a number of challenges throughout the length of the project, the most substantial ones are listed here. One challenge was the integration between the previous senior design team's ultrasound tracking program, the Vuforia software, and the augmented reality environment. Even after one integration went well, it often required multiple iterations to remove bugs and allow it to run properly. During the integration of these various softwares, another issue arose which centered around the lack of processing power. When running the ultrasound volumization and tracking programs simultaneously, their intensive hardware requirements caused us to have to limit the size of the ultrasound volume in order to allow the programs to run smoothly. Furthermore, the Vuforia software requires any application to be built on the HoloLens itself rather than on the computer, thus preventing the ultrasound volumization and holographic needle from working simultaneously on a single device. When porting the volumization software into augmented reality, we were able to successfully integrate the Vive tracking program from last year's senior design team. However, this method still requires a number of accessories that must be calibrated to work properly, which can take a significant amount of time to set up. The largest challenge of this project was simply from a limitation around ultrasound data itself. Because we were only able to collect a single 2D slice of ultrasound data at a given time, the user has to pass over the same region again in order to update the reconstructed volume. While there were a number of challenges along the way, our senior design team was able to create 2 systems that addressed the main goals of our project. The first part is seen here with the ultrasound volumization. Essentially, as the Vive tracker, which is the large black object seen to the left, tracks the physical location of the ultrasound probe, our volumization program is able to generate a volume from live ultrasound data, all while simultaneously projecting this volume in line with patient anatomy via augmented reality. This helps to improve the interpretation of the ultrasound data by giving our user a 3D perspective of relevant anatomy, rather than having the user having to rely on a solid understanding of cross-sectional anatomy to identify specific structures. Additionally, the variable transparency helps to highlight relevant anatomical structures such as nerve bundles, muscle boundaries, and blood vessels. As seen by the teal bar to the left, this would be where the subject's ulna bone would lie. Rather than seeing a white circle, such as in traditional 2D ultrasound techniques, the user can clearly see a transparent 3D space where the ulna bone would be, thus removing the clinically irrelevant anatomy and decluttering the user's view while still indicating where this feature would be should the user need it. In addition to the successful integration of augmented reality and the Vive tracking, the program is also able to accommodate a number of ultrasound scan depths and ultrasound probes, thus allowing it to be used to visualize a number of different areas of the body.
The second system we developed is an application on the HoloLens that will use the integrated cameras to detect the fiducial attached to the needle, track its movement, and project a hologram of a rendered needle in alignment with the real needle shaft. The image on the left captures how the projected needle will look in the application once the black fiducial is detected. As you can see, the projection is aligned with the needle shaft and is visible despite the needle tip being inserted into a phantom. The attachable fiducial was designed to fit snugly around the dimensions of a standard echogenic needle used in nerve blocks today, so that it will not shift during the procedure and does not contact the needle shaft. This piece could easily be manufactured as a disposable part out of medical-safe plastic in order to maintain the current weight. We believe having this hologram throughout the procedure will eliminate the current needle tip visibility issues that occur with standard ultrasounds.
We believe this product has multiple potential impacts for the future of ultrasound procedures. First and foremost is the advancement in the use of augmented reality for medical applications. This product demonstrates how augmented reality technology can be successfully used in a clinical setting. We also believe that in the future, this product will improve patient outcomes and reduce morbidity for ultrasound-guided procedures. Finally, we think that it will significantly decrease the learning curve of these procedures for new clinicians. The picture to the right shows how the final project looks like being used. There are still some future developments that can be made to it. Future developments of the project include optimization. Although the software works, it consumes more memory and GPU than intended. Optimizations could be made to have it run smoother. There are still some refinements that could be made to the needle tracking system. More specifically, we can improve the alignment of the needle hologram with the physical needle. Finally, we have to combine the needle tracking and ultrasound volumization systems into a single functional application. We have accomplished a lot over the course of the semester, and we are proud of our project and the learning experiences we had while working on it. Finally, we would like to recognize Dr. Todd Clapp, Dr. Stu Tobit, Stephen Su, Chad Edel, and Brandon Garr for their support and advice throughout the project. Additionally, we'd like to credit last year's team, Deanna Ball, Benjamin Farkas, Stephen Su, and Jane Matthews, for the foundational work they did. Finally, we want to thank our senior design instructor, Dr. Ellen Brianna Purse, and our TAs. None of this could have been done without you guys, and we are deeply grateful. Thank you for listening to our presentation, and have a good day.